you basically have a system that has some secret information that gets leaked through the correlation with some observable event, right? And we saw three types of these systems. We saw a small software program, this password checker, in which the leakage was small at the beginning, but then it was bigger due to this timing information. And then we saw two anonymous communication systems where the basically we're trying to hide the correlation between the observation on the network and the originator in this system by using some probabilistic actions. And then the key question was that, okay, there is this leakage, we cannot completely prevent it. So the question is, how can we quantify it? How can we say, is the leakage small or big? Or how can we compare two systems, for instance, say that the system is one system is better than the other? So we started discussing this simple idea of information theoretic channels. So these channels, they are probabilistic systems that take as input secret information, and as output they have this observable information. So what observable is, of course, depends on our model and what exactly we consider as capabilities of the adversary. And the behavior here was probabilistic, and it was described by this matrix of conditional probabilities, where each row is a secret. So each row here is a secret. So in the Dynamic Purpose example is the identity of the sender of the message. Yeah, that's better. Very good. Much better. All right. So the rows are secrets, the columns are observations, and then the value here itself gives you the probability to have this observation when this is the actual secret in your system. Okay? And then we saw that when the coins are fair, this is what you get in this simple scenario of three cryptographers. When the coins are biased, you get something that's a bit less symmetrical. Okay? And now the key point of this correlation, to understand what's going on, is that because of these conditional probabilities and because of the relationship between the output and the input, when I see an output, starting from some probability distribution that gives me some information about the input, right? So I have some information about the input given by some probability distribution. When I see an output, this gets transformed into a posterior distribution. So this is like saying, I know that say Frank sent a message with probability 1/2 because he's a guilty guy, like suspicious looking guy. Then after seeing this observation, my initial probability of 1/2 now became even more. And now I'm saying, okay, this is for sure Frank. It's this correlation. So the study of quantitative information flow looks at these changes of posterior and prior probabilities and tries to quantify, okay, how much leakage was caused of the system by reasoning about these probabilities. All right. Okay, so observable transforms a prior into a posterior. Okay, so let's see a bit in more detail how this is done. So now this is our system. Okay, this dynamic system, and let's say that I have this prior. Okay, so this is Frank. So has high probability because I know that he sends messages often, right? So it's a guy who is a priori susceptible to to be the initiator of the message. And then there are two other people running the protocol. So for them, I know that. So together they have the remaining 1/2, but between them they look equally right. Okay, and I run this dynamic purpose protocol with the biased points, and I know that the channel looks like that. Okay. So now remember that this channel has conditional probabilities. Okay, so it has the probability to produce this output. So 1/3 is the probability that this guy here, right, Frank, produces 001. It's funny because every time I say Frank is doing something and then looks. So we're gonna do this. I like it. It's good. All right. Now from this, the first step into. So now the question is how I transform priors into posteriors. Right? This is just simple probability theory, nothing too complicated, but it's nice to see happening. So the first step is to create the joint distribution between secrets and observations. All right. So now this is a different matrix than this that I produce by multiplying. I'm taking this vector here and I pass it through all the columns here and multiplying it. All right. So this comes. It just says that the probability to have this user and this observation together, all right, will be given by the probability of having this user multiplied by the probability to produce the observation when this is the sample, right? So this is standard. So by doing this on every row, the big matrix here is just one joint probability distribution, right? This matrix had n, okay, n is the number of secrets, n probability distributions, all of them were conditional. Okay, every row here was a probability distribution. Now this matrix here that I got by multiplying this with this vector is a semi-probability distribution, the big thing, okay? And each cell here giving me what is the probability of having this secret and this observation together, right? Okay, now from this, I go up the columns and I create the marginal output distribution. All right, now I'm going to figure out what is the total probability of getting this observation, right? And this will be simply the sum of all these, all right? So this is, so the probability of giving 0, 0, 1 will be the probability of 0, 0, 1 and this plus 0, 0, 1 and 1 and then so on, okay? So the sum of every column will give me the marginal, okay? So now I see that here 0, 0, 1 has this probability, 0, 1, 0, and 1, 0, 0 have 1/4, and 2 over 9 is the following one. Okay, and then the final step is I take now so by using the Bayes law, okay, I know that the posterior, so now what I want is, I want the posterior probability of every user given the observation. All right, this is my posterior. This tells me how likely is every user given my observation. And this will be given by the joint divided over the marginal, all right? So I just need to take this one and this one, divide one with the other, and this creates back a posterior probability, all right? To see the relationship between this, so this is the prior secret probability, okay? This is what I knew before the protocol, all right? What was I was suspecting, right? This, some general information about my secrets when I started the protocol. And then when I see the specific output, okay, now I'm focusing on a single output here, right? And I'm gonna take each one of these values of the column, right? Divide it by this number here, and this is gonna give me how likely now is every user, okay, after the observation. And we see that these two users, so because I'm focusing on this observation, and because this observation happens more often from this user than from these users, right? So you see that the probability of Frank here producing 001 is higher than the other two guys, okay? So this means that when I see 001, it's natural that given this observation, right, the posterior probability given this observation will make Frank look even more guilty because, yeah, I saw an event that is produced by Frank by higher probability. And so this is indeed the case. If I look at the posterior probability for this event, it will have a higher value than 1/2 here for Frank and lower value for the other two guys. All right. Also, look at the other two guys. So they had same probability to begin with, and the probability to produce this event was also similar for both of them. Right? So essentially, this observation did not change anything with respect. So the relative probability between the two didn't change because this observation is equally likely to be produced by any of them. So when I see it, so their total probability changed, but between them, there's still 1/5. Right? So this is pretty standard. But the next thing is that by just looking at this matrix and nothing else, and starting from the prior, I can work it out and create a posterior distribution. Okay. But of course, now I don't have just one posterior, right? I have one posterior for each one of these observations. Okay. So now the question is, what's going on exactly? So yeah, you can see that there is some leakage, right? I see that this observation make Frank look a bit more guilty. The other observation will make him look a bit more innocent. But how can I quantify this overall? Right? I see that there is some leakage, but is it big? Is it small? Okay. Yeah, let's see also the examples that we have in we saw this morning, and see how we can construct the channel matrix from them. So this was the original program that was checking these passwords and was checking every single bit of the password before announcing OK and fail. Right? So the timing information here was not really important, and the output was just the OK and fail. All right. Now remember that the input of our channel is the secret information, right? It's not necessarily the input of some program, it's what I consider secret information. So although here, although the user types some string here, I see that as a parameter of the system, what the actual user typed, and the secret of my channel, so what I put as a channel input, is the actual password, right? So the secret is not what the user typed, we don't care about this, it's not secret information. Definitely. And what we care about protecting and measuring the leakage of is the actual password. So I'm gonna take the number of possible passwords as a channel input. Okay. So what are we gonna do? Okay, we consider, I mean, for the sake here of writing everything down, very short, of course, example where so the password consists only of 3 bits. So these are the 8 possible configurations of passwords, right? So it's of course a small, not very interesting system where the user can only have one of 8 passwords. And let's assume also that the user string is this one. So this is what the user entered, right? So he entered 110, and he let the system go. Okay, so what's going to happen? So the system has 2 observations, OK and fail, right? And we see that for 7 out of 8 of the possible passwords, the program is going to output fail, right? And just 1 password is going to output OK, right? And this was, our initial intuition that, all right, this is not too bad because, I mean, everything but 1 password is mapped to the same observation. So from the observation here, it's not possible to say anything between among these secrets. But of course, there's just a single one that completely gives out the password. And in terms of channel, again, these are the inputs, these are the conditional probabilities, and this is a simple deterministic program. So deterministic programs have just zeros and ones as probabilities. Every secret will give fail with probability 1 and OK with probability 0, except the actual secret that was the actual password that was given by the user, 110, that's the opposite. Okay, we'll use OK for sure and fail never. Okay, so there are no probabilistic behavior here. So privacy comes from the fact that most of the secrets, so all of them but one, is mapped to the same one. Well, now if we look at a slightly modified program, okay, so now remember the difference was that I'm going to exit as soon as I find the first failure. So now timing depends on the secret, okay, and I'm going to consider this as an actual observation. So now the observations it's not just failure or OK, but it's a tuple of failure and timing, and OK, there's no time because the time in the case of the OK will always be the same, right? So to arrive at the OK, I need to complete the full loop, so there's no timing info there. Okay, and what's going to happen? There are going to be now 4 passwords here that fail and fail right away, okay, immediately, because the user entered 1 here and the password was already wrong in the first place. Okay, so these are mapped to 1 observation. There are 2 passwords that fail on the second bit, 1 password that has 2 bits correct and only fails on the third one, and of course 1 password that completely passes. Right? So you see sharp contrast between this here picture, where you can visually see that okay, there's less leakage going on, everything's collapsed to the same observation, and completely different picture here where different classes are mapped to different observations. And now the channel is bigger because we have more observations, and again it's deterministic, so these four secrets here are mapped to probably 1 to 1 observation, 2 secrets are mapped to this observation, probably 1, and so on. Okay, so it's a slightly more complicated channel, but still. All right, so this should be reasonably simple. I mean, just going through it so that it's, it's understandable how exactly. Because I mean, we're gonna, soon enter formulas that try to quantify all this. But I mean, there's nothing like really magic happening. So the important thing is to understand how the behavior of the system is mapped and transferred here into these channels. All right. So now I have my system, I have my matrix, and I have seen already how I can go from prior probabilities to posterior probabilities. Now the last element is okay, but since the beginning, so since the first goal of this lecture was quantify how we can quantify things, right? And so far, right, you can see these probabilities, but I haven't quantified anything, okay? So how I'm going to do that? So I'm going to use notions from information theory, right? That is useful concepts that were invented long before security and all that, but they are very useful because they inherently talk about correlation, communication, and all this. All right, so I guess many of you probably have seen this in a course of information theory. Maybe, I mean, it doesn't really matter because I'm not going to enter into a lot of detail about any of those. The important is to understand what these notions try to capture, right? So now I have some random variables or some event with probabilities. So the entropy is a measure of the degree of uncertainty about this event, right? So I have some probabilistic phenomenon that might have many outputs and some probability distribution governing them. So an entropy, and there are many notions of entropy, okay, but in general, they show some degree of uncertainty about this event. Okay, so if this probabilistic event has one outcome with very high probability, or there are no probabilities at all, because it's probably one of outputting something, then the entropy will be very low because there's not enough uncertainty. I don't need to know anything. I don't need any more information to figure out what will be the outcome of my system. While on the other hand, if there are a lot of different possibilities, okay, and many of them have substantial probability, or I have no probabilistic information between them, it's just uniform, then entropy is high, okay, because it's hard to predict what's going to happen. And this is, if you imagine, this is a natural way. So since I have this notion of uncertainty, it's quite natural to use it to measure the vulnerability of the secret. All right. So how easy is the adversary to discover the secret? If the secret has high entropy, then an adversary will have trouble discovering it, while with low entropy, an adversary will be able to guess it easily. Okay. So this entropy is the basic thing. It just talks about just one variable, okay? And you could maybe imagine this as being the secret in our case. Then the second thing that comes into second notion from information theory is mutual information. So what's going on now here? So now I have two different random variables, right? So I have S that I care about, and then O that is something that's correlated to S. And then mutual information tells you how correlated is S to the outputs of O. All right? So, so again, it's not that important to see. So, let's take a second back, and before even talking about mutual information, let's go to this entropy. Okay? So we saw the entropy of this secret, okay? And so in order to arrive at mutual information, I'm going to use an auxiliary notion here, which is the conditional entropy of S given O. Right? So now I have two dependent variables, right? And again, I want to mention entropy, but not entropy of S itself, but entropy of S, assuming that O was given, right? So, I mean, before here I just had a random variable without any extra information. Now I have a random variable, and somebody tells me the value not of this variable, but of some other variable. All right? Now, if these two random variables happen to be completely uncorrelated, this is useless. All right? So I want to find my secret, and somebody told me what's the weather in Tokyo. Okay, these are two random variables, probably uncorrelated. So the fact that I know the one doesn't tell me anything about the other. Okay. So in this case, the entropy. So maybe I have a secret that has high entropy, and the entropy given some observation will also be high, right? Well, on the other hand, maybe the second observation, okay, that somebody gives me is exactly the secret that I want to find out, right? So, or it's determinedly connected to it. So I want to find a secret, and somebody tells me, secret +1. So I can very easily, there's high correlation, I can very easily work it back. So maybe I have high entropy in the beginning, maybe this is high, but after knowing this observation, the entropy now is very low, right? And now what I care about, if you think about it, is not really how much entropy is, because entropy might be smaller or maybe high or low, depending on how well the adversary is informed to begin with, right? Maybe an adversary already knows my password, so okay, he's very well informed about that. Or maybe the passwords I choose are very weak, so the adversary knows that I'm choosing 1 to 3 with very high probability, so the entropy is low. Okay, but that's not, if you think about it, that's not really a problem of the password checking program, right? This is an orthogonal thing. I mean, it's an important thing that, of course, we need inform users that they need to choose strong passwords. But what kind of probability of choosing passwords you use is not what I want to measure here. What I want to measure is how good is the password checking program, right? So this brings me to the notion of mutual information, which is simply the entropy. So mutual information between two things, the secret and the observation, will be simply how much entropy is left from my secret if I subtract the entropy of the secret after the observation. Right? And this is called leakage. This is how much entropy, not how much entropy the system has, but how much it loses because the system exists. How much worse we are because we use this system. Right? So it could be, for instance, that my password is very weak and this is, say, 0. Right? So my entropy is very, very small to begin with. Okay, this will be 0, this will also be 0, and the leakage will also be 0. So actually I didn't lose anything. I mean, I was bad to begin with. Okay? I didn't lose anything because of my system. And what I want to quantify is the effect of the system. Alright? So is it clear? So still I'm kind of high level here in what entropy actually is. Right? So I'm going to see two concrete examples of entropies. But in both cases, I mean, this is the general picture on this area of quantitative information flow. So I'm going to pick some notion of entropy, right? I'm going to look how I can define it in a way that makes sense in the prior case, how I can define it in the posterior case, and then I'm going to subtract the one of the other. And this is going to be my measure of the leakage of the system. Right. Questions here?
I do have one. What's the so leakage is what, a number between 0 and 1, or?
So it will, of course, depends on what's the choice of these numbers, right? So in general, it's not going to be between 0 and 1. We're going to try to keep it positive so that it makes sense. But then depends on our choice. In general, it will be in the most common case a number between 0 and the log of the different observations we have in the system.
So you do have like some kind of a scale that tells you that 0 is good or it's bad? Or?
Yes, so you can view it, I mean, often you choose then the entropy to think about in terms of bits, right? So kind of average case of how many bits you lose. So without meaning that you really lose specific bits, like the first bit or the second, but on the average, how many bits. Okay, so you can view it that way. But depending on the notion of entropy, maybe the scale is completely different, and maybe, But that's a good thing because we're going to talk about numbers, right? And then numbers don't say much unless we have a notion of, what do they mean, right? So, I mean, I could, write down a formula and tell you that, okay, this is a great formula and the leakage is 5. I'm going to say, okay, 5 is good, right? But then, of course, to be able to say whether 5 is good or not is a different story. Okay, it's an important story, and because of that, I'm gonna introduce the entropy notions starting from some operational characterization. Right. So I'm not gonna just pop out a formula and say this is a formula, use it. So I'm gonna start by some operational scenario and say what is my attacker, what he's trying to do, and the entropy will be a measure of how successful the adversary is in doing this. And from this, you will have some intuition of what the number means. So this is first answer. Okay, that I mean numbers sometimes they matter, and you should be able to say what they mean. And then, of course, there's a second important thing that probably I'm not going to have time today to discuss about. It's going to be tomorrow. That sometimes you're not really interested in the number, like the leakage itself, as a number, like to really say what it means that this is 5. Okay, but maybe what you're interested in is comparing two things. Okay, so I'm giving you, so you have a system, right? It works in some way. Okay, like this password example, for instance. Okay, so you have this password example. So you're a password program, you're using it, but you're not very satisfied of the performance that it has. Okay, so you're saying, yeah, it's my system is very overloaded, and so I come to you and say, no, but I have this great program that runs faster than all this. Okay, so now in that case, you might run the analysis and say, look, but the leakage of the one is higher than the other. Okay, and even more importantly, if you start with this system, so you say that you had such a system, or maybe some other system that was not leaking that much, okay, but was leaking something, and I do the opposite thing. So I come to you and I say, look, you have this system, right? You can replace it with my other version that I can prove to you that never leaks more than your version, right? Then in that case, the actual number doesn't really matter. I mean, whatever 5 is, I can prove to you that my system will leak less. Okay, so sometimes you don't really care about characterization, but what you care is comparing channels, right?
Yeah. In this password example, there is a clear correlation between the time it failed and the byte we consider the password.
Yes.
So we have quite a clear intuition on what could be an algorithm to break, to find the password. Your measure of entropy, or what you're talking about, measure of leakage, doesn't care that there is a straight correlation between this part of the numbers.
Exactly.
And to which extent it...
so this is a very good observation. So
can we still have certain algorithm that will be probabilistic to crack the password?
Yes, so that's not necessarily. So in general, all these information theoretic approaches just look at the correlation between two things, right? So they really don't care about whether it's feasible. Okay, so this will tell you that, so if you come with a high leakage in such a system, right? This will tell you that it is possible, right, in general, by some infinitely capable computational power, right, to map out, because there is some correlation, right? If there is correlation, in principle you should be able to find it. Okay? However, it might be computationally infeasible. Like for instance, you might have some crypto program that's completely deterministic, okay, because there's no probabilities in crypto, and you can run such an analysis and say, I mean, of course, it will be hard to do the numbers, but then the leakage will be there because everything is deterministic, right? I mean, if you start with a key and you have some data, the encrypted version will be different every time, right? So there will be a perfect correlation between output and input. And of course, you want that because you want to be able to decrypt, right? If there is no correlation, then using the encrypted thing, you wouldn't be able to decrypt, right? So if you use an information theoretic analysis like that, it would tell you that you have high leakage, because it completely forgets about computational aspects, right? So this is, this is something to have in mind. I mean, it doesn't, correlation doesn't always mean that it's feasible to exploit it. But yeah. Right. Right, so, okay, we arrive at this concept of operational interpretation, right? So the point here to make is that there's several notions of entropy, and people have been using it to analyze systems and say, okay, I measured the sun entropy of my system and it's 5, and somebody else will come and say, no, the real entropy of my system is 7 and whatever. And okay, yeah, you can use many notions of entropy. They will make some sense. But of course, the key question here in security is to say, okay, what does this entropy notion actually tell me about my system, all right? So one approach that makes sense is to start with some operational interpretation. Right? So you start with some adversary that has a specific goal about doing something in your system. Okay? So you model an adversary that has some kind of attack, right? And then you come up also with a way to measure the success of this attack. Okay? And this often will give you an entropy measure that essentially is tied to this operational scenario. Right, so this was this comes from the work of Kostas from 2007, and there are also other works that look at this. But the idea is exactly so what I said, that you have a model of yes/no questions, and then you have an adversary that defines the form of the question, and then you measure the success of this attack, and you consider always that the adversary will have best strategy. So if he can have various strategies, he's going to use the best, and you try to quantify, okay, how successful this adversary is. Right? So let's see an example. So let's say that the adversary can. So remember that the adversary, what he can do is he can ask questions of some form. Right? It's up to him to define the form. So one possibility is that the adversary uses questions of the form, is the secret in some set, right? So I can come up with some sets, okay? And then I ask the question to this oracle, is a secret in this set, okay? And the measure of success is the expected number of questions needed to find the value as in this best strategy, all right? So, of course, whether this operation scenario makes or not make sense in your in a real case, depends on the actual scenario. But you can imagine that an adversary picks some set here and then runs some attack, and if the secret is within the set, the attack will be successful. So the adversary wants to guess the secret in order to perform this success as quickly as possible. All right? Let's take an example here. So the secret just belongs to this small set here of letters. And of course, an important thing is that when an adversary tries to guess a secret, he's going to take probabilities into account, right? So if a secret is highly likely, then I'm going to guess it first. So let's say now in this case that there are three classes of secrets here. So the first two have probability 1/4 each. Here, the second two have probability 1/8, and the remaining ones they share the remaining probability, so they all have 1/16 each. Okay? Another question is, given the scenario, and with an adversary that can pick arbitrary sets, right, and ask the question, is the secret within the set? How quickly can this adversary, in average, find out the secret? So, for instance, a simple strategy, very dummy, would be start asking about every secret individually. All right. So I can ask, is the secret A? Does it belong to the singleton set A? Then the oracle responds yes or no. Then if it's yes, okay, I won. I'm happy because I found it immediately in just one step. If not, I continue with B and C and so on. Right. And you can see that this will make sort of tree, and sometimes I will be lucky and I will find the answer high in the tree. Sometimes I will be unlucky and I will find the answer low in the tree. Okay? But then if I just do this, in this dummy way, one by one, you will see that the cases where I will be lucky and I will be high, I will find it quickly, will be few, and most of the time I will be spending a lot of questions to do that. On the other hand, the best strategy, so this can be proved, it's not that hard, is that the best strategy for the adversary is to split each time the search space in two subspaces with probability masses as close as possible. So every time I'm asking a question, the two answers should basically split my space in as balanced as possible probability events. Right? So for instance, I can start with a set A, C, E, F. Right? So I'm picking one secret from this class, one secret from this class, and two secrets from this class. Okay? So they all combined have probability 1/2. And I'm asking this question: is the secret in this set? So the answer is quite variable because it gives me, in both cases, it gives me a lot of information. It brings me in a subspace of total probability 1/2 in each case. Yeah.
When you say an event in a class, what do you mean by class? The events that have the same probability?
Yes, sorry, yeah. By class, I mean, yeah, the first two here, they both have probability 1/4. Yeah, class. Sorry, yeah. Yeah, this is what I mean. I took one. So I just wanted to make basically the probability of this set the same or as close as possible to the probability of the remaining elements, right? So I mean, you can easily see that A, C, and EF together will have the same probability as B, D, and G together, right? So now when I get an answer, an affirmative answer that this is indeed in this set, I continue, right? So now I know that I'm within A, C, E, and F. Now the second question I'm gonna ask, when I know that I'm inside here, I'm gonna again do the same, right? But now A has high probability, so itself within this set here, itself. So I'm gonna split the 1/2 total probability here into two fourths, right? But A itself has 1/4, so I'm gonna keep A on one side and CEF on the other side. And I'm going to ask the question, the second question will be, is a secret within CEF? Okay? And if I have a negative answer, then I know the secret must be A, because it belongs to this set and it doesn't belong to this set, so it must be A. Right? So we see that A here will be, so if the secret is A, I'm going to need just two questions to figure it out.
The question is exactly the same as looking for the optimal search tree.
Sorry?
Creating this tree. Is it the same as looking for an optimal search tree?
Yes, so this tree is exactly the optimal strategy of the adversary. So the optimal way of splitting of figuring out these sets here in order to minimize the expected length of this. Right? This is indeed the best strategy. Right, and then the key point here is that.
I think there's a problem because there's no choice.
Sorry?
That's okay.
So, yeah, so you can see that the clever part here is that elements with high probability will need a smaller number of questions, while elements with small probability, right, so the smaller probability of an event is, the more questions that we need to find it. And the cleverness of this is that because these events have smaller probability and I care about the expected length, well, if something is very unlikely to happen, I don't care because we'll need more questions to answer. Right?
Can you always build this tree? If you have a uniform probability, there is always a tree to do.
Yeah, there's always, I mean, it might not be possible to find exactly, to split it exactly in half, right? Yeah, I mean, sometimes, but this would be like the best you could do. If you could do this, that would be really the best. Okay? So the entropy is going to give, I mean, it might be the best strategy or an approximation of the best strategy. Yeah. Right, yeah.
Is it always the case that the most probable elements are
higher, yeah. Yeah, I need to build it this way because I care about how many questions will be needed on average, right? So if something has high probability, I want to have it high in the tree because it corresponds to a big probability mass, right? So
what's the time complexity you computed?
All this is so. This is the beauty of information theory. You don't care about complexity. Yeah, I don't know. I don't think it's that. I mean, complexity on the number of elements. I don't think it's that.
That's okay. Because you split over all subsets.
No, but you can order the elements.
No, I'm sure you can order the elements.
Maybe you find the first split, but at the beginning maybe it's optimal, but then you have other subsplits which are maybe not optimal.
You look, I mean, the principle for the top root, the root could be everything, or there's no up.
Yeah, it's true. So this set here would be everything that is as close as possible to.
If it's extremely close, it could be 2 to the n possibilities. How do you prevent that you have to all of them? I don't know. What's the
I'm
question?
sure that somebody will
There's
have
probably
answered
random
this.
algorithm to do that.
It's actually the best solution ever, because then the best strategy is difficult to be found. Nice.
Yeah, well, nice. If this is the kind of attack we care about, right? Because this is, I mean, this is an attacker that somehow benefits by these questions, right? And by benefit, I mean that, I mean, maybe his actual attack succeeds if you know the set that he chosen, maybe he's given access to to some system or something like that, right?
It's true that if the complexity of building such a tree is very high, then it's pointless because it cannot be computed.
No, so, wait a second. So the entropy that we're going to define, okay, will be what is the success of this. So we'll measure the success of this attack, okay, and will be for sure an upper bound on. So I mean, it will be for sure that on